Tonight we turn our attention to quantum entanglement, a phenomenon where particles exhibit correlations that persist regardless of the distance between them. This is not mysticism or pseudoscience. Entanglement is an established feature of quantum mechanics, observed in thousands of experiments and now used in emerging technologies. The correlations are real, measurable, and precisely predicted by quantum theory. We will move through these ideas without excitement or urgency. Entanglement has acquired a reputation in popular culture as mysterious or even magical, but it is physics, carefully observed, mathematically described, and thoroughly tested. The correlations do seem strange from a classical perspective, and they raise genuine questions about the nature of reality. But they are neither mystical nor speculative. We approach this subject with patience and clarity, distinguishing carefully between what experiments show and what remains open to interpretation. Before we can discuss entanglement itself, we need to establish what physicists mean by certain fundamental terms. These concepts involve quantum states, measurement, and correlation in ways that require careful explanation. Entanglement is a quantum phenomenon where two or more particles share a joint quantum state, such that measurements on one particle are correlated with measurements on the others, regardless of the spatial separation between them. When particles are entangled, measuring a property of one particle, such as its spin direction or polarization, instantaneously determines the corresponding property of the other particle, even if they are separated by large distances. This does not mean that measuring one particle causes the other particle's state to change in a way that propagates as a signal. The correlation is instantaneous, but it cannot be used to transmit information. No signal travels from one particle to the other. Both particles together exist in a single quantum state that encompasses both of them. Measurement reveals correlations that were established when the particles became entangled, not created at the moment of measurement. A quantum state describes the condition of a quantum system. For a single particle, the quantum state might specify properties like position, momentum, spin, or polarization. But the state does not always assign definite values to these properties. Instead, it specifies probabilities for different measurement outcomes. A particle in a superposition has probabilities distributed across multiple possible outcomes. Only when measured does a definite outcome occur. For entangled particles, the quantum state describes both particles together. It is not simply a combination of individual particle states. The joint state is non-separable, meaning we cannot describe each particle independently. The state of the whole is more than the sum of the parts. This non-separability is what creates the correlations we observe in measurements. Correlation, in general terms, means that two quantities are statistically related. If knowing one helps predict the other, they are correlated. Correlation does not necessarily imply causation. Two events can be correlated because they share a common cause, even if neither directly causes the other. In classical physics, correlations arise from shared histories or common origins. In quantum entanglement, correlations have a different character. They are stronger than any correlation achievable through classical means. If we try to explain quantum correlations by assuming particles carry hidden information, predetermined values for the properties we might measure. We find that no such explanation can match what quantum mechanics predicts and what experiments observe. This is the essence of Bell's theorem, which we will explore in detail. Measurement outcomes when dealing with entangled particles appear random for each particle individually. If you measure the spin of one particle in an entangled pair, you get up or down with certain probabilities. The outcome appears random. You cannot predict which result you will get. But when you compare your result with a measurement on the other particle, you find correlations. If you both measured spin in the same direction, your results are correlated in specific ways predicted by quantum mechanics. Non-local in physics refers to correlations or effects that are not confined to a small region of space. Entanglement exhibits non-local correlations. The measurement results are correlated regardless of distance. This does not mean signals travel instantaneously between particles. It means the quantum state describes both particles as a unit, and measurements reveal correlations encoded in that joint state. The distinction between correlation and communication is crucial. Entanglement creates correlations between measurement outcomes, but it does not allow communication. You cannot use entanglement to send a message faster than light. Individual measurements appear random. Only when you compare results through ordinary communication limited to light speed or slower do the correlations become apparent. The no communication theorem in quantum mechanics proves this rigorously. Classical correlations can be strong, but they are limited. Imagine a person writes left on one card and right on another, puts them in envelopes, and sends one envelope to you and one to a friend far away. When you open your envelope, you instantly know what your friends will find. The opposite word. This is perfect correlation, but it is classical. The information was determined when the envelopes were prepared. Each envelope carries definite information. Quantum correlations differ in subtle but crucial ways. For certain combinations of measurements, quantum mechanics predicts correlation strengths that exceed what any classical scenario can produce. Bell's theorem quantifies this difference. Experiments testing these predictions consistently show correlations matching quantum mechanics and exceeding classical limits. This is the empirical signature of entanglement. What entanglement is not requires emphasis to avoid common misconceptions. Entanglement is not faster than light communication. You cannot use entangled particles to send messages instantaneously. Individual measurement outcomes remain random, and no information about one measurement is available at the other particle's location without classical communication. Entanglement is not action at a distance in the sense of one measurement causing a change that propagates to the other particle. The correlations are already present in the joint state. Entanglement is not mystical, does not involve consciousness, and has no connection to telepathy or other paranormal claims. These definitions form the conceptual foundation. Entanglement is a correlation between measurements on particles that share a joint quantum state. The correlations are stronger than classical physics allows, instantaneous but not usable for communication, and thoroughly confirmed by experiments. Understanding entanglement requires distinguishing it carefully from superficially similar but fundamentally different phenomena. To understand how entanglement was discovered, debated, and eventually established as accepted physics, we must trace the development of ideas from quantum mechanics' early days through decades of theoretical and experimental work. Quantum mechanics, developed in the 1920s, predicted phenomena that seemed strange even to its creators. Particles exhibited wave-like behavior. Measurement outcomes were probabilistic. Properties did not have definite values until measured. These features troubled many physicists, including Albert Einstein, who accepted quantum mechanics' empirical success but questioned whether it provided a complete description of reality. In 1935, Einstein, together with Boris Podolsky and Nathan Rosen, published a paper presenting what became known as the EPR paradox. They considered a thought experiment involving two particles that interact and then separate. According to quantum mechanics, the particles become entangled. Measuring a property of one particle instantaneously determines the corresponding property of the other, regardless of distance. Einstein and his colleagues argued this seemed to imply either that information travels faster than light, violating relativity, or that the particles must have possessed definite properties all along, even before measurement. If they had definite properties before measurement, quantum mechanics' probabilistic description was incomplete. The particles carried hidden variables specifying their properties, which quantum mechanics simply failed to describe. Einstein famously described entanglement as spooky action at a distance, expressing discomfort with apparent non-locality. He believed nature should be local, that events at one location should not instantaneously affect distant locations. He also believed in realism, that particles have definite properties independent of measurement. Together, these beliefs, local realism, led Einstein to view quantum mechanics as incomplete. Niels Bohr and others defended quantum mechanics, arguing that Einstein's assumptions about reality and locality were precisely what quantum mechanics challenged. They maintained that quantum mechanics is complete, and that properties like spin do not have definite values until measured. The debate remained philosophical for decades because both sides agreed on quantum mechanics predictions. They disagreed on interpretation, not calculation. The situation changed in 1964 when John Stuart Bell, a physicist at CERN, proved a remarkable theorem. Bell showed that if local hidden variables exist, if particles carry predetermined values and influences propagate no faster than light, then certain combinations of measurements must satisfy inequalities called Bell inequalities. Quantum mechanics predicts violations of these inequalities for entangled particles. This made the debate empirical. Experiments could test whether nature obeys Bell inequalities or violates them. Bell's work was theoretical, but it opened the door to experimental tests. If experiments showed violations of Bell inequalities, local hidden variable theories would be ruled out. Quantum mechanics would be vindicated, and we would have to accept that nature is fundamentally non-local in the sense that measurement outcomes exhibit correlations not explainable by local hidden variables. The first experiments came in the 1970s and 80s. Alain Aspect and his collaborators in France performed groundbreaking tests using entangled photons. They measured photon polarizations at different angles and compared the correlations. The results violated Bell inequalities, matching quantum mechanics predictions. Local hidden variable theories could not explain the observed correlations. These early experiments had limitations. Potential loopholes allowed skeptics to argue that hidden variables might still work if certain assumptions were relaxed. The locality loophole concerned whether measurements on the two particles were truly separated in space-time, whether information could, in principle, travel from one measurement to the other at light speed or slower. The detection loophole concerned whether your undetected particles might bias the results. Over subsequent decades, experimenters refined their techniques, closing loopholes one by one. Experiments separated detectors by large distances and ensured measurement choices were made quickly enough that no light speed signal could coordinate them. Detectors improved to capture nearly all particles. By the 2010s, experiments closed all major loopholes simultaneously, leaving no room for local, hidden variable theories to escape. These loophole-free experiments, performed by multiple groups worldwide using different methods, consistently showed violations of Bell inequalities. The correlations in entangled particles are stronger than any local realistic theory can produce. Quantum mechanics accurately predicts the observed correlations. This is not interpretation or philosophy. It is measured fact. The 2022 Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their work on entanglement and Bell inequality tests. The Nobel Committee recognized that experiments established entanglement as real and ruled out local, hidden variable theories. Entanglement moved from being a philosophical puzzle to an experimentally confirmed phenomenon and a resource for new technologies. The history shows how science progresses. A conceptual debate that seemed purely philosophical was transformed into an empirical question through Bell's theorem. Experiments tested the predictions, initially with limitations but improving over time. Multiple independent groups using different techniques reached consistent conclusions. The evidence accumulated until the case became overwhelming. Entanglement is real. Its correlations are non-local in a specific sense, and local realistic theories cannot explain nature's behavior. This history also illustrates the importance of distinguishing what experiments show from how we interpret what they show. Experiments definitively rule out local, hidden variable theories. They confirm quantum mechanics predictions for entangled states. What this means for the nature of reality, whether it implies genuine non-locality, whether particles have properties before measurement, what happens during measurement, remains debated among those who study quantum foundations. but the empirical facts are established. Core concepts: what entanglement is. Understanding entanglement requires examining how entangled states are created, what happens when we measure them, and why the correlations differ from anything classical physics can produce. Entangled states are created when particles interact in ways that couple their quantum properties. One common method uses a process called spontaneous parametric down conversion. A photon passes through a special crystal. Occasionally the photon splits into two photons with correlated polarizations and opposite momenta. The two photons are entangled. Neither photon has a definite polarization on its own, but the pair exists in a joint state where their polarizations are related. Another method entangles electron spins. Two electrons brought close together can have their spins become correlated through quantum interactions. Once entangled, measuring the spin of one electron provides information about the spin of the other. Atoms, ions, and even larger quantum systems can be entangled through carefully controlled interactions. The key feature of an entangled state is non-separability. The quantum state describing both particles cannot be written as a simple product of individual particle states. For non-entangled particles, we could say particle A is in state X and particle B is in state Y, and describe them independently. For entangled particles, the state is fundamentally joint. We cannot assign independent states to the individual particles. They must be described together. Mathematically, a simple example of an entangled state involves two particles that can each be in one of two states. Call them up and down for spin, or horizontal and vertical for photon polarization. An entangled state might have the property that if one particle is measured to be up, the other will be down, and vice versa. But before measurement, neither particle is definitely up or down. The pair is in a superposition of both possibilities. When we measure one particle, we get a definite outcome, say up. The state of both particles is now determined. The other particle, when measured, will yield down. This seems to suggest that measuring the first particle instantly affected the second, but no signal travelled. The joint state already encoded the correlation. Measurement reveals what was implicit in the entangled state. Crucially, individual measurements appear random. If you measure one particle of an entangled pair repeatedly in many trials, you get up sometimes and down sometimes, with probabilities determined by the quantum state. You cannot predict individual outcomes. The randomness is genuine as far as quantum mechanics is concerned. But when someone else measures the other particle in the same way, their results correlate with yours. If you got up, they get down, or vice versa, depending on the specifics of the entangled state. The correlations appear perfect in certain measurements. For photons entangled in polarization, if both observers measure polarization in the same direction, their results are perfectly anti-correlated. One gets horizontal, the other vertical, or vice versa, every time. This perfect correlation holds regardless of distance. The photons could be separated by meters, kilometers, or in principle, light years. the correlation persists. But when measurement directions differ, the correlation weakens. If one observer measures polarization vertically while the other measures at 45 degrees, the results are partially correlated but not perfectly. Quantum mechanics predicts precisely how the correlation depends on the angle between measurement directions. Bell's theorem concerns the pattern of correlations across different measurement angles. Why do correlations matter? In classical physics, correlations between separated objects arise because they shared a common cause or carried information from a common origin. Imagine a factory produces pairs of shoes, one left and one right, and ships them to opposite sides of the world. When you open your box and find a left shoe, you instantly know the other box contains a right shoe. This is perfect correlation, and it arises from classical information established at the factory. Quantum correlations are different. The pattern of correlations for different measurement angles cannot be reproduced by any classical mechanism where particles carry hidden information determined at their source. Bell's theorem proves this mathematically. The specific correlation pattern quantum mechanics predicts and experiments observe exceeds what local hidden variables can produce. Entanglement is a resource. It can be used for tasks impossible with classical correlations alone. Quantum cryptography uses entanglement to detect eavesdropping. If someone intercepts entangled particles, they disturb the quantum state in detectable ways. This allows secure key distribution. Two parties can establish a shared random key guaranteed to be private. Quantum teleportation uses entanglement to transfer quantum information. An unknown quantum state can be transmitted from one location to another using an entangled pair and classical communication. The original state is destroyed in the process, and information travels no faster than light. Classical communication is necessary. But the transfer works because entanglement provides a quantum channel. This is not teleportation in the science fiction sense of moving matter. It is the transfer of quantum information about a state. Entanglement is monogamous in a specific sense. If two particles are maximally entangled with each other, they cannot be entangled with any other particles. Entanglement is a limited resource. You cannot share unlimited entanglement among many particles. This monogamy distinguishes entanglement from classical correlations, which can be freely shared and copied. Distance independence is another key feature. Entanglement correlations do not weaken with distance. Photons have been entangled over hundreds of kilometers on Earth and between Earth and satellites in space. The correlations remain just as strong as at short distances. This suggests entanglement is not mediated by any field or force that diminishes with distance. It is a feature of the joint quantum state itself. Decoherence causes entanglement to degrade over time. Entangled particles interact with their environment. Stray photons, air molecules, thermal fluctuations. These interactions couple the entangled system to many environmental degrees of freedom, effectively measuring the particles and destroying the delicate quantum correlations. Maintaining entanglement requires isolating particles from environmental disturbances. In practical applications, entanglement must be used quickly before decoherence destroys it. Entanglement is real, measurable, and strange. It creates correlations that cannot be explained by classical physics. Measurement outcomes are random individually, but correlated when compared. The correlations are instantaneous but cannot transmit information. These features are not speculative. They are confirmed by thousands of experiments. Entanglement is an established phenomenon, a resource for technology, and a window into quantum mechanics foundations. Bell's theorem is a mathematical result that clarifies what entanglement implies about nature. Understanding the theorem and its experimental tests is essential for appreciating why entanglement matters. Bell's theorem addresses whether quantum correlations can be explained by local hidden variables. A local hidden variable theory assumes two things. First, particles carry hidden information that determines measurement outcomes. Before measurement, each particle has definite values for properties we might measure, even if quantum mechanics does not describe those values. Second, influences propagate no faster than light. What happens at one particle cannot instantaneously affect what happens at another distant particle. These assumptions, realism about properties and locality about influences, constitute local realism. Einstein favoured local realism. He believed particles should have definite properties independent of measurement, and that physics should be local. Hidden variable theories attempted to provide such an account underlying quantum mechanics' probabilistic descriptions. Bell showed that local hidden variable theories make specific predictions that can be tested. Bell derived inequalities, mathematical constraints on correlations that any local realistic theory must satisfy. The inequalities concern measurements on entangled particles with detectors set at different angles. For three measurement angles, a particular combination of correlation strengths is constrained. If local hidden variables exist, the combination cannot exceed a certain value. This is a Bell inequality. Quantum mechanics predicts violations of Bell inequalities for entangled states. For certain measurement angles, quantum correlations exceed the classical bound. The difference is not large, but it is definite and measurable. If experiments show violations, local hidden variables are ruled out. Nature does not operate according to local realism. The simplest version, the CHSH inequality, involves two observers, call them Alice and Bob. Each has two possible measurement settings. Alice can measure at angle A1 or a 2. Bob can measure at angle B1 or B2. They perform measurements on many entangled pairs. For each pair, Alice and Bob independently choose settings. They record whether their results agree or disagree. The CHSH inequality states that a specific combination of correlation coefficients, calculated from how often results agree or disagree, must be less than or equal to 2 if local hidden variables exist. Quantum mechanics predicts this combination can reach about 2.8 for appropriate angles. This violation is the signature of entanglement's non-classical nature. Experiments testing Bell inequalities must satisfy stringent requirements. The locality condition requires that measurement, choices, and outcomes at Alice's location cannot influence Bob's outcomes for his measurement completes, and vice versa. This requires spatial separation and fast measurement switching. If Alice and Bob are close enough, or if measurement settings are chosen slowly enough, a signal could travel between them at light speed or slower, potentially coordinating outcomes without violating locality. Early experiments could not fully satisfy the locality condition. Measurements were fast, but detectors were close enough that light could, in principle, travel between them during measurements. Later experiments placed detectors far apart, kilometers or more, and used rapid random switches to choose measurement settings. These ensured that no light speed signal could coordinate the outcomes. Even with such precautions, violations of Bell inequalities persisted. The detection loophole concerned whether all particles were detected. If detectors miss some particles and undetected particles differ systematically from detected ones, local hidden variables might still explain the observed correlations among detected particles. This loophole required detectors with very high efficiency, capturing nearly all particles. Early detectors were not efficient enough. Technological advances eventually produced detectors that closed this loophole. The freedom of choice loophole concerned whether measurement settings were truly random and independent of hidden variables. If hidden variables influenced which settings were chosen, correlations might be explained without non-locality. Closing this loophole required settings determined by processes independent of the particle's common past. For instance, using light from distant quasars to choose settings, ensuring the choices were uncorrelated with the entangled particle's history. By the 2010s, experiments closed all major loopholes simultaneously in single experiments. Multiple groups achieved this using different techniques: superconducting qubits, trapped ions, entangled photons. All showed clear violations of Bell inequalities, matching quantum mechanics predictions. Local hidden variable theories could not explain the results under any combination of reasonable assumptions. The implications are profound. Nature does not operate according to local realism. Either particles do not have definite properties before measurement, violating realism, or measurement outcomes at distant locations are correlated in ways that cannot be explained by local influences, violating locality, or both. Quantum mechanics does not specify which assumption to abandon. Different interpretations make different choices, but experiments definitively rule out the combination of both realism and locality. This does not mean information travels faster than light. The no communication theorem in quantum mechanics proves rigorously that entanglement cannot transmit information. Individual measurement outcomes remain random. Correlations become apparent only when results are compared through ordinary classical communication, limited by light speed. What Bell's theorem and experiments establish is that the correlations themselves have a non-local character that cannot be reproduced by local mechanisms. Bell's theorem transformed entanglement from a philosophical puzzle to an empirically testable phenomenon. It provided clear predictions distinguishing local hidden variable theories from quantum mechanics. Experiments tested these predictions systematically, closing loopholes and refining techniques over decades. The verdict is clear. Nature violates Bell inequalities. Quantum correlations are real and non-classical. Entanglement is not an artifact of incomplete understanding. It is how nature operates at the quantum level. Entanglement is not merely theoretical. It has been created and measured in laboratories worldwide, using various physical systems and demonstrating correlations over increasing distances. Examining specific examples illustrates the phenomenon's reality and the precision with which predictions match observations. Photon pair entanglement is the most common experimental realization. The standard method uses spontaneous parametric down conversion in a nonlinear crystal. A pump photon, typically ultraviolet, enters a crystal with special optical properties. Occasionally, the pump photon splits into two lower energy photons, called signal and idler, that emerge in different directions. Conservation laws ensure the two photons have correlated properties. The two photons can be entangled in polarization. If the pump photon has appropriate polarization, the signal and idler photons emerge in a superposition of polarizations. Neither photon has definite polarization, but they are related. If one is measured to be vertically polarized, the other is horizontal, or vice versa. The joint state is entangled. These photon pairs are used in Bell inequality tests. Detectors placed in the paths of the signal and idler photons measure polarization at chosen angles. The angles can be set independently and rapidly. Thousands or millions of photon pairs are measured and correlations are calculated. The results violate Bell inequalities, confirming that the correlations cannot be explained by local hidden variables. Alain Aspect's experiments in the early 1980s were groundbreaking. Using cascaded atomic transitions in calcium atoms to produce entangled photon pairs, Aspect and colleagues measured correlations with rapidly switched detector angles. The results clearly violated Bell inequalities. Although locality and detection loopholes remained, the experiments provided strong evidence for entanglement's unclassical nature. Modern experiments have refined the technique. Entangled photons have been generated and measured over long distances. Photons transmitted through optical fibers maintain entanglement over kilometers. Free space transmission extends this to tens of kilometers. In 2017, China's Mikius satellite distributed entangled photon pairs between ground stations over 1,200 kilometers apart. The correlations persisted, violating Bell inequalities even at this vast separation. Entangled ions provide another system. Trapped ions, individual atoms held in electromagnetic fields, can be controlled with extraordinary precision. Two ions are placed close enough to interact, entangling their internal electronic states or their motions. Once entangled, the ions can be separated and their states measured. Correlations match quantum predictions. Ion traps allow loophole-free Bell tests. Ions can be detected with near-perfect efficiency, closing the detection loophole. Rapid measurement sequences and sufficient separation close the locality loophole. Experiments using entangled beryllium and magnesium ions have demonstrated clear Bell inequality violations with all major loopholes closed. Superconducting qubits used in quantum computing research can also be entangled. These are tiny superconducting circuits that behave quantum mechanically. Two qubits coupled through electromagnetic interactions become entangled. Measurements on the qubits show correlations characteristic of entanglement. While maintaining entanglement in superconducting qubits is challenging due to decoherence, advances in qubit design and error correction are improving coherence times. Electron spins in solid-state systems provide yet another platform. Quantum dots, semiconductor structures confining electrons to small regions, can hold entangled electron spins. Nitrogen vacancy centers in diamond, defects where a nitrogen atom substitutes for carbon, can trap electron spins that are entangled with nuclear spins. These systems are attractive for quantum technologies because they operate at relatively high temperatures and can be integrated into devices. Quantum teleportation experiments demonstrate entanglement's utility. In the first demonstration in 1997, researchers at the University of Innsbruck teleported the quantum state of a photon to another photon using entanglement. The procedure requires 3 photons, the one carrying the state, to be teleported and an entangled pair. A joint measurement on the original photon and one of the entangled pair projects the other member of the pair into the original photon's state. Classical information about the measurement outcome is sent to the receiver, who uses it to recover the state. The process transfers quantum information without physically moving the particle. Teleportation has since been performed with atoms, ions, and across increasing distances. It is not science fiction teleportation of matter, but a genuine quantum information protocol. It relies crucially on entanglement and demonstrates that entanglement is a resource enabling tasks impossible classically. Quantum cryptography exploits entanglement for secure key distribution. In the E91 protocol proposed by Arthur Eckert, 2 parties share entangled photon pairs. They measure photons at random angles. By comparing a subset of results publicly, they check for eavesdropping. Any interception disturbs the entangled state, introducing detectable errors. Once confident the channel is secure, they use their correlated results to establish a shared secret key for encrypting messages. This protocol has been demonstrated in laboratory and field trials, providing provably secure communication. Distance records for entanglement continue to extend. Ground-to-satellite entanglement has been demonstrated, as has satellite-to-satellite entanglement relayed through ground stations. These experiments paved the way for global quantum communication networks. The correlations remain strong regardless of distance, limited only by photon loss and decoherence, not by any weakening of entanglement itself. The consistency across systems and scales is impressive. Photons, ions, electrons, superconducting circuits, and atoms all exhibit entanglement when prepared in appropriate states. The correlations match quantum mechanics predictions quantitatively. Bell inequality violations are observed across platforms, experimental designs, and distances. This universality demonstrates that entanglement is a fundamental feature of quantum mechanics, not an artifact of specific systems or methods. These real-world examples show entanglement is not abstract or speculative. It is created routinely, measured precisely, and used in applications. The correlations are exactly as quantum mechanics predicts. Attempts to explain them with local hidden variables fail. Entanglement is real, non-classical, and an established part of our understanding of nature. Entanglement connects to many areas of physics and technology, influencing quantum information science, cryptography, computing, and our foundational understanding of quantum mechanics. Quantum information science treats quantum states as carriers of information and entanglement as a resource. Just as classical information theory quantifies bits and communication channels, quantum information theory quantifies qubits, quantum bits, and the entanglement they share. Entanglement is measured in units called e-bits. The amount of entanglement determines what tasks can be performed with a quantum system. Quantum computing leverages entanglement as a computational resource. A quantum computer manipulates qubits in superposition and entangled states to perform calculations. Certain algorithms, like Shor's algorithm for factoring large numbers or Grover's algorithm for searching unsorted databases, achieve speed-ups over classical algorithms by exploiting entanglement and interference. The quantum advantage arises from manipulating many entangled qubits in parallel. Building functional quantum computers is extraordinarily challenging. Qubits must be isolated to prevent decoherence while remaining controllable for manipulation. Entangling gates create entanglement between qubits, but environmental interactions destroy it. Quantum error correction codes use entangled qubits to protect against errors, but require many physical qubits to encode a single logical qubit. Despite challenges, small quantum processors with dozens of qubits have been built, demonstrating entanglement-based computation on simple problems. Quantum cryptography uses entanglement for secure communication. Quantum key distribution protocols establish shared secret keys guaranteed secure by quantum mechanics' laws. Any eavesdropper disturbing entangled states introduces detectable anomalies. Commercial QKD systems are deployed, though practical challenges like transmission losses and device imperfections limit range and speed. Entanglement-based QKD offers advantages over other protocols, particularly in verifying security against certain attacks. Foundations of quantum mechanics are deeply concerned with entanglement. The EPR paradox, Bell's theorem, and experimental tests address questions about reality, locality, and determinism. These are not merely philosophical, they concern what the world is like at its most fundamental level. Entanglement's non-classical correlations challenge our intuitions about separability and independence of distant objects. Different interpretations of quantum mechanics handle entanglement differently. The Copenhagen interpretation treats measurement as fundamentally important, with entangled states collapsing upon measurement. Many worlds interpretation posits branching, measurement creates branches where different outcomes occur, and entanglement links branches. Pilot wave theories maintain particles have definite positions with non-local influences coordinating outcomes. Each interpretation accepts entanglement's empirical reality but offers different ontologies. The measurement problem in quantum mechanics concerns when and how superposition gives way to definite outcomes. Entanglement complicates this. When a measurement device becomes entangled with a system, the combined system is in superposition. At what point does definite measurement outcome emerge? Decoherence provides partial answers. Interaction with environment effectively measures the system, suppressing interference. But decoherence does not select specific outcomes, only suppresses superposition. The no communication theorem proves rigorously that entanglement cannot transmit information faster than light. This reconciles entanglement's instantaneous correlations with relativity's prohibition on superluminal signaling. The proof shows that local measurements on one part of an entangled system yield random results. No manipulation of one system can signal to the other. Correlations appear only when results are compared, requiring classical communication at light speed or slower. Entanglement in many particle systems is an active research area. Large entangled states involving dozens or hundreds of particles exhibit complex correlations. Some quantum systems, like those near quantum phase transitions, develop long-range entanglement. Understanding how entanglement scales with system size and how it relates to emergent properties is crucial for condensed matter physics and quantum field theory. Decoherence theory explains how entanglement is lost through environmental interactions. A quantum system is never perfectly isolated. Interactions with surrounding particles, fields, and thermal fluctuations entangle the system with its environment. This entanglement effectively measures the system, decohering superpositions. For macroscopic objects, decoherence is nearly instantaneous, explaining why we do not observe macroscopic superpositions. Maintaining entanglement requires isolating systems from environments, a central challenge for quantum technologies. Black hole information paradox involves entanglement in subtle ways. When matter falls into a black hole, it becomes entangled with the black hole's internal states. If the black hole evaporates through Hawking radiation, information about the infallen matter seems to be lost, violating quantum mechanics' unitarity. Recent work suggests information might be preserved through subtle correlations in the radiation, involving entanglement between early and late emitted photons. This is speculative, but it shows entanglement's relevance to fundamental problems in quantum gravity. Entanglement connects quantum mechanics to information, computation, cryptography, measurement, interpretation, thermodynamics, and even quantum field theory and gravity. It is not confined to a narrow corner of physics, but permeates our understanding of quantum systems. This centrality reflects entanglement's status as a defining feature of quantum mechanics, perhaps the defining feature that distinguishes quantum from classical physics. As we move towards the closure of our discussion, we can restate gently some of the central ideas we have explored. Entanglement is a quantum phenomenon where particles share correlations that persist regardless of distance. When particles are entangled, measurements on one are correlated with measurements on the other instantaneously. These correlations are real, measurable, and precisely predicted by quantum mechanics. Individual measurement outcomes appear random. If you measure an entangled particle, you get a result that seems unpredictable. But when someone else measures the other particle in an appropriate way, your results are correlated. The correlation appears only when you compare results through ordinary communication. No information travels faster than light. The no communication theorem guarantees this. Bell's theorem proves that these correlations cannot be explained by local hidden variables. If particles carried predetermined information and influences propagated no faster than light, certain correlation patterns would be impossible. Quantum mechanics predicts those patterns. Experiments observe them. Local realistic theories are ruled out. Experiments testing Bell inequalities have been performed thousands of times using different systems: photons, ions, atoms, superconducting circuits. Results consistently violate Bell inequalities, matching quantum predictions. Modern experiments have closed all major loopholes. The evidence is overwhelming. The correlations do not weaken with distance. Entangled photons separated by hundreds or thousands of kilometers still show perfect correlations. This distance independence suggests entanglement is a feature of the joint quantum state, not mediated by any signal or field that diminishes with separation. Entanglement is created through interactions that couple quantum properties. Photons split in crystals, ions brought together in traps, electrons interacting in solids. Many systems can be entangled. Once entangled, the particles share a non-separable quantum state. Neither particle can be described independently. They must be treated as a unit. Decoherence causes entanglement to degrade. Interaction with the environment effectively measures the system, destroying delicate quantum correlations. Maintaining entanglement requires isolating systems from disturbances. In practical applications, entanglement must be used quickly before it decoheres. Entanglement is a resource for quantum technologies. Quantum cryptography uses entanglement for provably secure communication. Quantum teleportation uses entanglement to transfer quantum information. Quantum computing uses entanglement to perform certain calculations more efficiently than classical computers. These applications are not science fiction. They are demonstrated in laboratories and early commercial systems. What entanglement means for the nature of reality remains debated. Does it imply genuine non-locality? Do particles have properties before measurement? How should we think about instantaneous correlations that cannot transmit information? Different interpretations answer differently, but the empirical facts are clear. Entanglement is real, its correlations are non-classical, and local hidden variables cannot explain it. Entanglement seems strange because it differs from anything in classical physics. Classical intuition suggests that distant objects are independent, that information cannot appear instantaneously elsewhere, that correlations arise from shared histories. Entanglement violates these intuitions in precise, measurable ways, but it is not mystical. It is physics, carefully studied, mathematically described, experimentally tested, and technologically applied. We have moved through these ideas slowly, building understanding from definitions through history to experiments and applications. Entanglement is subtle, involving quantum states, measurement, and correlation in ways that require careful thought, but it is grounded in observations that are clear and consistent. Entanglement is an established feature of quantum mechanics, confirmed by evidence and used in emerging technologies. We have now travelled through the essential concepts of quantum entanglement, how entangled states are created, what correlations they produce, why those correlations cannot be explained by classical physics, and how Bell's theorem and experiments established entanglement as genuine and non-classical. We have seen that entanglement, while strange from a classical perspective, is thoroughly tested and now used as a resource in quantum technologies. There is no need to retain every detail. Entanglement involves concepts about quantum states and measurement that differ fundamentally from classical intuitions. Understanding develops through patient attention to what experiments show and careful thinking about correlations and causation. You may have drifted in and out as we spoke, and that is entirely natural. Each section we discussed was intended to stand on its own, so that wherever your attention rested, you encountered ideas that were complete in themselves. Entanglement reveals that nature operates in ways our everyday experience does not prepare us for. Particles separated by vast distances exhibit correlations instantaneous yet not usable for communication. These correlations are stronger than anything classical physics allows. They have been measured precisely and found to match quantum mechanics predictions exactly. This is not mysticism or speculation. It is tested science, reproducible and real. We close gently, without urgency, as we began. The concepts we explored are grounded in decades of theoretical and experimental work. Entanglement is one of quantum mechanics' most distinctive features, the phenomenon that most clearly separates quantum from classical physics. It is strange, real, and now harnessed for new technologies. These ideas will remain where they are, available for reflection, should you wish to return to them.